Okay, I don't know if it's recording yet, but I can also do this. Let's do it in read mode. There we go. How about that? So this just goes over, this is talking about the terminology that we're going to review. And you guys may know this terminology, but some of it's a refresher. And it was certainly a refresher for me. Zoom out on this a little bit, see if it will. There we go. All right. Multi-view drawings are created by configuring points, lines, and planes, okay, to create views. And a view could be like, think about the front view of your house. If you had a drone, you could zoom around the top and you could see the top view of the house, the right side view, the back view. Of course, not the bottom view of a house, right? But we do have a slab drawing. But if you think about a part, think about a die. You know, if you had a cube, how many sides are there to that cube? There are 6 sides to a cube. So imagine that you could actually have 6 different views of anything. And we know that by, they're all 90 degrees to each other. So we're going to use that kind of perspective. Now, points or locations. And we're going to have in AutoCAD, there is a 0, 0, 0 point. It's 0 in the X, 0 in the Y, and 0 in the Z, which is our 3D. So when we're in 2D, it's 0, 0, 0 in the X and 0 in the Y. So X always comes first. And I'm going to tell you why. I remember X as the horizon and Y to the sky. The sun comes up in the east, and then it goes, you know, to the sky, right? So the X always comes first. So when you see a number like this, it is a coordinate to locate that point. It is 2 away from the origin in the X and 3 away from the origin in the Y. All right, not always do we draw something like this. We may just start to draw it out in the middle of space, but some of these exercises are going to tell you start drawing at 2, 2, and that's 2 in the X, 2 in the Y. Well, what if we go to the left or down? We're going to look at that now. So this is just an example of what these coordinates would look like. And if you can see these, I want you to particularly look at these. These are all 0 in the Y, and the numbers are correlating the color of the X-axis and the color of the Y-axis. The color of the Z-axis is blue, and it's the same in 3D modeling. So in the X, at this point, it's not moved. In the Y, it's not moved, so that would be right here. It's moved 1 in the X and 0 in the Y. So that's a horizontal line. That would be a horizontal line from here to here if it did not raise up in the Y axis. So all of these are going to have 0 in the X. All of these are going to have, 0 in the Y. They don't raise up, right? But they have numbers in the X. And notice that it's on a grid system. It's called a Cartesian system. So it's like a grid. And so they would be equidistantly spaced. Inches, millimeters, feet. Over here, we have 0 in the X, so that line goes straight up. It does not move left or right. 0 in the Y does not move up and down. So we can still give coordinates for things that are horizontal or vertical as opposed to, you know, at an angle from our 0, 0 point. If I drew a line from here to here, I would have an angle. Don't hesitate to ask a question or restate what I say in a different way so that it makes difference, it makes sense to you. Now, there are some terms that we're going to learn, and one of them is coincident. Coincident means that 2 points, 2 lines, like if I had 2 lines, they share the same endpoint. That endpoint is coincident. Coplanar means they lie on the same plane. So these would be coplanar in the x plane. You know, they're all in alignment. These are in alignment in the y plane. And if I had two lines that came together at 1, 2, they would be coincident at that point. All right, so we were talking about how to go. What if we go to the left? What if we go down? If I say 2, 3, it's always going to go to the right and up. So there are positive and negative quadrants, you guys. So the way that I remember this is can I go right on red in Texas and not get a ticket? Yeah, I can do that. So that's a positive thing. Anything to the right is positive. If I go to the left, can't take a left on red in Texas, I will get a ticket. That'd be a negative thing, right? What if I make more money? That goes up. That's a positive thing to me sometimes, unless it throws me into another tax bracket. If I make less money, that goes down. So in this quadrant, it's left and down from relative to the 0, 0 point. And you're going to find that when we draw something, I may draw a line, and let's say this is not 0, 0, and I'm just starting right here. If I draw down into the left of that line, it's relative to that point. I'm going down into the left, so that would be a negative number. Negative x, comma, negative y. So this one would be negative x, positive y. Positive x, positive y to the right and up. And then positive x, negative y over here. So we have, imagine every endpoint of whatever you draw, when you're drawing the next point, from that point where you left off, think about, are you going down? That would be negative. If you're going up, that would be positive. To the left would be negative. To the right is positive. So we always start, remember, with the horizon and move to the sky. So x, comma, y. And it doesn't matter if it's positive or negative, x, comma, y. If you type in 0, 0, it's going to go back to your origin, where those two axes come together. Any questions on that? So up and to the right is positive. If you can just remember that, up and to the right is positive, then you're in good shape. The others are negative. In 3 dimensions, you know, we were talking about, we had this x and y on that screen, but there's something that we're not seeing, and that's the depth of whatever we're drawing. And that's when we get into 3D modeling, we will pull that whole boundary to make a depth to that whatever we've drawn. So that's our z-axis. In the first part of this semester, for a long time, we're going to be working in 2D, and the z-axis gives us our 3D, our depth. All right. I was actually going over these with my next level class, because there are some terms in here that are absolutely used in that software. Colinear. That to me means that not only do the points on the line, they're on the same line. They lie on the same line. But let's say I had another line that went from here up here. They will always be on the same path. Let's say this is an arrow and I shot it into the air. And I shot it at a bullseye. Let's say I threw a dart or something. It had a path, right? So if I draw another line, all points on that line will be on the same path as this one. That would make those on the same line, or collinear. And they could be, yes, they would be parallel as well, right? But with 0 offset. So they could also be from here out. It could be have some space in between them, but they would not be offset from each other. They're on the same line, at the same angle, on the same trajectory or path. Non-collinear could be at an angle to each other. Parallel, we know what that is. It's going to have the same angle, and both endpoints will have the same spacing to the endpoints on the other line. The other line could be longer, but it will be equidistant from this line all the way, no matter what angle. And we're kind of used to that term. A spline is a smooth curve, and it is tangent or smoothed out as if there's no corner anywhere where they converge. Where it turns direction, there's no corner there. It's like a railroad rail. You know, if the railroad rail had a sharp in any place, the train would derail. And so it has to be smoothed out, and all curves have to blend. It's like taking a block of wood and sanding around on the edge of it. You don't want to feel any kind of corners. It's all very smooth. And there's some other terms for that we'll talk about in a second. Non-collinear. These two lines are not on the same path. That would create an angle. And they're at an angle to each other. And they don't even have to touch down here. They don't have to have this coincident point. But when we do touch and have an endpoint that's coincident and on both lines, at the end of both lines, that's called a vertex. So a point at the end of two lines is a vertex, okay? Now, we all know what an intersection is. That's when lines cross each other, right? And so that's different than a vertex. Now, one that we are going to use is perpendicular. And any two lines that are absolutely 90 degrees to each other, you might see a square right here, meaning it's a right angle. That's absolutely 90 degrees. That's called perpendicular. And we're not really going to use these angles, but anything less than 90 degrees is called acute little angle. That's how I remember it. It's an acute angle. Obtuse is greater than 90, but less than 180 degrees. So if we had the planes of a house, they would all be perpendicular to each other, and the house would be, hopefully, you know, if we had a perfect ground, it would be perpendicular to the ground. We have complementary angles that add up to be 90 degrees, no matter what they are. They will add up to be 90. Supplementary add up to be 180. And this is something that we are going to use. If you have an intersection, the angles opposite each other are always going to be equal. Opposite angles will always be equal. And then we have adjacent angles. Adjacent angles add up to be 180 degrees. So these are side by side, which is what adjacent means. And these are opposite angles, opposite across that intersection. Now, there are two ways to talk about circular objects or curved objects. We could have, anytime we have a full circle, it gets this diameter symbol. So let's look at that symbol and see what that means. If you drew a line from anywhere on this circle, and it's a straight line, and it goes straight through the center, the absolute perfect center, all the way through to the other side, that would be the outside diameter measurement. And that's what that symbol looks like. It looks like this circle with a line straight through the center. Now, half of a circle from the center, anywhere around this circle, if it's a true circle, is half of the distance all the way across. So that is called a radius. And we put an R in front of that to specify that it is a radius. So normally, and this is a rule, and I don't like that they show this, we never put a radius on a full circle. But it's just showing that that's half of a diameter. We're going to talk about the rules of when do we have to use a radius, when do we have to use a diameter, and when can we use either one, and why would we do one over the other. We'll talk about that later. Now, another thing to talk about in smoothing out, you know, we talked about those curves that were all smooth in the railroad track. There's something called tangency, and it's a relationship. If you had a snowman, those two, or two basketballs, they're touching at the apex or the very highest point or the very lowest point of those two balls. You know, if I took a basketball and set it down on the ground, That would be its tangency. It would be touching at the apex. So I could move this circle right here anywhere around here, and it would always be touching at that apex. Now, when you talk about lines going to a circle, that's not, okay, so maybe they're just stuck there and they can rotate and you really can't see it. Or I could rotate this around here. That is a fixed point to fix one circle to another. That's why we're even talking about this, because if I want them to be tangent to each other, they will never overlap. Okay? Now, when I want a line to be tangent to a circle or an arc, it is going to be at an angle. This line will be at an angle so that it's absolutely smooth and there will be no edge where they touch. There won't be a little divot and there won't be a bump out. It will be absolutely smoothing out like that railroad track. And so if I had a tangent line, that just means that a circle is stuck to this line at its highest point and not overlapping it, if that makes any sense. It's not crossing it at all. It's touching on the very outside point. We use tangency a lot when we want to, like a wood block, if I had another line over here, I would actually sand that down so that that's absolutely smooth and we would not see any transition from the line to the curved surface. It would be absolutely smooth. So there's a snap that we're going to make things tangent to each other. We're going to make it smooth, and that's why we're talking about tangency. So the way that we draw things in AutoCAD, we can express tangency, and it's a rule that will make it draw it a certain way for us. Concentric. Concentric could also be two coincident center points. They're on exactly the same spot. And if you had like two cylinders, their axes, their 3D axes would be absolutely on top of each other. That's concentric. So they're on center. If you're eccentric, you're a little bit off center like me, or keep Austin weird, right? There are lots of eccentric people here. You can really see that these don't have the same center. Okay, you guys know what squares and rectangles are. Those are quadrilaterals or four-sided polygons. So in AutoCAD, we will draw a rectangle. REC is the alias, and we could draw that as a square. We can draw that with certain size. Now, triangles, we could have a right triangle, and you see that would be perpendicular right there. It's a right angle. Equilateral is all 60 degrees, or it will have three equal angles. And saline means that there are no angles at all that are the same. And I'm going to tell you in a minute why we're even talking about this. But, you know, if you had a polygon that has 6 sides, a hexagon, it's like a bolt. And I'm just going to tell you this because I'm a mechanical person. If I drew a circle and I drew this hexagon, snap to the center of that circle, and I let the points define, you know, if I do this at a 1/2 inch and I let the point touch there and stopped right there, that would not be a 1/2 inch bolt. That would not have a 1/2 inch head. That is the distance across the points. And this, so that's called inscribed. It's inside the circle that you would draw. And that's how we define. So you have to draw things in AutoCAD to a certain size. You can't put a dimension on it and it change it like it does in a 3D modeler. Can't do that. You have to draw it to size. And so we draw this circle, and this wouldn't be the way that I would do this one. If you go circumscribed, that means outside. I just remember inscribed is inside. The other way is outside. This is the distance. If this were a 1/2 inch diameter of a circle all the way across, then from one flat to the other, that would tell me what size wrench to go and get. If that's a 1/2 inch from one flat to the other, I would go and get a 1/2 inch flat wrench, right? This is called across the flats, and this is across the points. And most of the time, we need to know the distance across the flats. So these are the other kind of polygons that we can have. and that just means it has multiple sides. Now we have cylinders, and that is a circular element. It has an axis, and that cylinder can have taper like a megaphone. So they don't always have to be the same diameter on each end. Coaxial cylinders right here. The axis will be coaxial. That means they have the same axis. Their centers would be concentric, and their center points would be coincident in each area. If you did cross sections all the way across, they would always be in alignment. If you had a plane, let's say I took a piece of rod and I set a board on it, it would be touching at the tangent point. That just means it's stuck down to it. And it could be at any angle. It could be anywhere around this cylinder. I don't know why we're really talking about these things, but you could have center planes that go through the axis. That's how we find the location of where these planes would go through this axis. This is more for 3D modeling. But we could also have a plane right in the center of a part. So this statement right here, symmetry, means that it's equidistant on one side as it is the other. It doesn't even have to, it could be two separate size holes. As long as they're equidistant, left and right, symmetric about something. So we are going to talk about symmetry a little bit. I don't like to use symmetry in drawings because it kind of, especially in this first class, we'll use it in the second mechanical class. And it just helps us not have to put so many dimensions on things, but I think it's important to learn that in the first class. Then we have 3D shapes of prisms, spheres. How do you dimension a sphere like that? You put in a spherical diameter, and you only need, an arrow pointing to it and an S and a diameter symbol, because it's that way in its depth, in its width, and in its height. It's the same dimension all the way around. So you only need one dimension for something like that. Same thing with the spherical radius. If you had a ball hitch on the back of your car, that would be a spherical radius because it's not a complete circle. All right, and that's what we've got for the first part of chapter 2. Does anyone have any questions?
None yet.